Hello. Today we are going to discuss synaptic transmission with using Goldman-Hodgkin-Katz equation, and we will mainly focus on the membrane permeability and membrane electrical potential changes during synaptic transmission. The chemical synapse is constituted of a presynaptic cell, a postsynaptic cell, and a synaptic cleft. In the presynaptic cells, there are synaptic vesicles which contain the neurotransmitters, and when the presynaptic cell is stimulated, usually by action potential, the synaptic vesicles fuse to the cell membrane, and neurotransmitters are released into the synaptic cleft. The synaptic cleft is a very narrow space. Neurotransmitters released into this space very quickly diffuse to the postsynaptic membrane, and they bind to postsynaptic receptors which activate the postsynaptic cell. Usually this activation leads to an action potential in the postsynaptic cell. There are other effects of postsynaptic receptor activation, but today we will basically focus on the postsynaptic cell depolarization and the formation of action potentials in the postsynaptic cells. When we look at the postsynaptic membrane potential during a synaptic transmission, we see that first there is a little depolarization occurs in the postsynaptic membrane, which then leads to fast depolarization phase, which is called the action potential, and then this depolarization turns into a repolarization, and the membrane potential goes back to its resting values. This initial depolarization, which actually triggers the action potential, is called the postsynaptic potential. We will mainly focus on this postsynaptic potential and how it happens via the synaptic transmission will be our main focus today. Postsynaptic membrane contains basically two types of receptors: the ionotropic receptors or the metabotropic receptors. Ionotropic receptors are basically ion channels. They are activated by binding of the neurotransmitter molecules. And when the neurotransmitter molecule binds to this receptor, the ion channel opens and membrane conductance changes. It's a direct and fast mechanism. Metabotropic receptors, on the other hand, uses an intermediary protein called the G proteins, and they activate an enzyme usually within the cell, which produces an intracellular messenger, which is called a second messenger, like cyclic AMP or IP3. No matter which receptor is activated, what happens is a change in the membrane conductance in the postsynaptic membrane. So the general wisdom, or the general explanation, is that membrane becomes more permeable to sodium, and as there is more sodium ion, the concentration of sodium is higher in the extracellular domain than it's in intracellular domain. The sodium diffuses into the cell, bringing positive ions and increasing the positive ions in the intracellular part of the cell, which charges the membrane, the cell membrane, as shown here, which is called depolarization. This is not an incorrect explanation. However, it's a little bit naive and problematic, incomplete explanation. It pretty much holds with action potential, but when we start to discuss the postsynaptic depolarization, we quickly run into trouble if we ask a few simple questions. For example, there is no known direct interaction between a receptor and a sodium channel. Receptors usually modulate sodium channels, but they never, as far as we know, they don't activate them. And also, well-known postsynaptic receptors, which are known to cause postsynaptic depolarization, ionotropic receptors like nicotinic acetylcholine receptor or some NMDA receptors or serotonin type 3 receptors, they are all non-selective cation channels, which means that they make the membrane permeable to sodium and potassium at the same time. So if membrane becomes permeable to both sodium and potassium, how come that sodium goes in but the potassium doesn't come out is a little bit confusing question and requires some scrutiny. On the left-hand corner, upper left-hand corner, you can see a typical postsynaptic depolarization without the action potential. Actually, here the action potential doesn't happen in the cell, and you only see the effect of the neurotransmitter release, which occurs during the blue horizontal bar, and of course the release is an instantaneous phenomena. Then whatever the neurotransmitter is released, either degraded by enzymes or taken by some special proteins back to the presynaptic cell. Through these mechanisms, the concentration of the neurotransmitter is decreased in a very short time. Thus, the action of neurotransmitter is quite limited within the synapse. So we represent this phenomena with this blue bar, the horizontal blue bar. And as you can see, at the time when the light blue arrow indicates, the cell is at its resting potential. Resting potential is usually equals or very close to potassium equilibrium potential or potassium nest potential. We will see the reason for this in a short while, but this is given as a fact, which means that the membrane is polarized like this, which is a negative membrane potential. If the intracellular side of the cell is negatively charged, then it means a negative membrane potential, which indicates that potassium has an outward influence, which pushes the potassium to the outside because of its concentration gradient, which is called a chemical potential. Sodium has a chemical potential which pushes it inward, and the membrane potential, electrical potential, shown here with the blue arrow, pushes both ions towards the intracellular. And as the membrane is at potassium equilibrium potential or potassium nest potential, which means that the blue arrow and the potassium's red arrow has opposite directions but equal magnitudes. So the potassium is basically in an equilibrium. There is no net driving force on potassium. However, for sodium it's not so, because both arrows, the blue and the red arrow, has the same direction, so sodium has a very big driving force towards the cell interior, which you can see clearly from here. Now, when the neurotransmitter releases and the ionotropic receptors opens up, there is a conductance immediately opens for both sodium and potassium, as the ionotropic receptors mostly non-selective cation channels. However, as there is no net driving force for potassium cannot move. Sodium, on the other hand, can influx to the inside of the cell, thus bringing in positive ions with it, which decreases this charging of the membrane. In turn, it decreases the membrane potential, which is called depolarization. You can see it on the upper left corner. The membrane potential does not go up, it goes towards zero, which means a decrease in the negative membrane potential. Be careful about that. And but at that moment, the potassium is not in equilibrium anymore, because the membrane is not at potassium Nernst potential, which means that now potassium is a driving force, which you can see an outward driving force, which means that immediately there will be a potassium flux. But the question is, which one is bigger? Because if one of those fluxes, sodium or the potassium influx or the efflux, is bigger, which means that there will be a net positive ion movement either from inside to outside or from outside to inside, which will either decrease the charging of the membrane, or increase the charging of the membrane. So we have to know which one is bigger. When we look at the situation, so for sodium, even if the membrane electrical potential decrease, it's still invert, and sodium has an invert chemical potential, the invert driving chemical potential, which means that but when you look at the potassium, it has an outward chemical driving potential, but the electrical potential is opposing it. So sodium is apparently has a more driving force. If the conductance for sodium and potassium is the same, because the flux depends on both the driving force and the conductance, not only one of them, on both of them. If the conductance for sodium and potassium is the same, then sodium flux will be bigger than the influx, will be bigger than the potassium efflux, outgoing flux, efflux. Okay? So which means that there is a net inward positive ion flux, which further decreases the polarization of the cell, which means further depolarization. However, as you can see, as the membrane potential decreases, the driving force on the sodium decreases, because one of the invert driving forces is decreasing, and potassium driving force is increasing because the opposing effect is decreasing. The opposing effect being the effect of the electrical membrane potential. Thus, the sodium current is decreasing and the potassium efflux is increasing. Eventually, at a certain membrane potential, they will be equal. As the influx and the efflux of the positive ions becomes equal, opposite directions but equal magnitude, which means that there is no net ion or charge movement across the membrane, which means that the polarity or the charging of the membrane will not change. This is a steady situation. If you think that the sodium gradient, concentration gradient, or the chemical potential, and potassium chemical potential is more or less the same, opposite directions but same magnitude, and the conductance for both ions is the same, then this should occur at zero membrane potential, electrical potential. However, this may not be the case. The conductances for sodium and potassium may not be completely equal, or the chemical potentials may not be exactly, the magnitude of the chemical potentials may not be exactly the same. So this steady situation may occur at a certain membrane potential, not at zero always. As you can see, at that stage, the membrane potential, when you look at the graph on the upper left corner, the membrane potential becomes stable at that situation. It cannot change. It reaches a steady point and it doesn't change. This is a steady state, by the way. It's not an equilibrium. It looks like an equilibrium, but it's a steady state, because the fluxes, sodium and potassium fluxes, are still continuing. The only thing that is zero is the net positive ion cation flux. At that moment, the neurotransmitter in the synaptic cleft started to decrease, and the channels, the ionotropic channels, close. So which means that the cationic conductance is gone now. Now what we are left with is a potassium current. This potassium current is the base current, which is responsible for keeping the basal membrane potential of the cell. Why we did not mention this while we're discussing the conductance induced by the neurotransmitter? Because when these ionotropic channels open up, the conductance is so big that this basal potassium conductance is kind of negligible. However, when this ionotropic channel closes because the neurotransmitter concentration decreased in the synaptic cleft, now all that is left is this basal potassium current. So it is what determines the membrane potential. So let's see what happens. What happens is that potassium has a net outward driving force at this stage. And there's no opposing ion flux because sodium ions cannot pass through the membrane. These are potassium channels. These basal channels are potassium channels. So only potassium can move, which means that now there is a net outward flux of cations, a net positive ion efflux, which charges the membrane. The membrane potential becomes more and more negative, and when it reaches the potassium nernst potential, the electrical effect and the concentration effect for the potassium, the chemical potential for the potassium and the electrical potential of the membrane cancels each out, and potassium has no net driving force at this stage, which means even if the potassium channels are open, so the conductance for potassium is there is no net driving force for potassium. Potassium does not move. And the membrane comes and stops at EK, the potassium nernst potential, or potassium equilibrium potential. That's why the resting membrane is at potassium nernst potential, which is around minus 80 millivolts. Let's rewind, go back to the steady situation, the steady state, which occurs during the synaptic transmission when the ionotropic receptors are ion channels were open and both sodium and potassium can move. However, we reached at a certain point, that the influx and efflux of the cations were equal and there was no net charge. And this occurs at a certain membrane potential, and we discussed that it can be at 0 millivolt or it can be some other potential. And what is this membrane potential which the steady state occurs? That's the question we have to answer. As we can understand, it depends on both the chemical potential of the ions and also the conductance of those membrane to those ions. To answer that question, we need the Goldman-Hodgkin-Katz equation. The Goldman-Hodgkin-Katz equation is simply a solution of this electrical circuit. Actually, this version of Goldman-Katz equation, Hodgkin-Katz equation, is not the real Goldman-Hodgkin-Katz equation. It's a simplification made by Hodgkin and Huxley. But it's a better tool for education, and it's easier to follow and mathematically less challenging. So I prefer it. But it's good enough for us. So let's concentrate on this modified Goldman-Hodgkin-Katz equation. Here the membrane is represented by a circuit. There is a capacitance, which is indicated by the Cm, which represent the charging of the membrane. And there are two voltage sources. Voltage sources are basically batteries. As you can see, the batteries, one of them is moving the positive ions. By the way, in physics, when we talk about electrical current, we always think about current is carried by positive charges. So one of the batteries drives the positive charges to the outside of the membrane. The other one is driving them to the intracellular site, as you can see by the polarity of the batteries. And each battery is connected to a changing or adjustable resistance, which we do not give the resistance values but the conductance values, represented by G. And each resistor represents an ion channel for that specific ion. And the membrane potential is the potential between the sides of both sides of the membrane capacitance, as shown here. So whatever the membrane potential should be to have a steady state situation, which means that the charging of the capacitance does not change, can be obtained by this equation, which is called Golden-Katz equation. It's a simple equation. You multiply the conductance for that ion and the Nernst potential for that ion. Nernst potential for that ion actually is the chemical potential. It's caused by the concentration difference between the intracellular and extracellular solution. Here we represent this driving force as an electrical driving force, but it's actually a chemical one. The potential is not electrical but a chemical, but it's represented here as with a battery. So and you divide this expression with the sum of all conductances. Let's go back and see what happened using during this synaptic transmission using this equation. First of all, during the resting phase, the sodium conductance is almost zero. So, which there's only potassium conductance, which means that the expression circled with red is basically zero, and the G sodium is basically zero, which leaves us with GK times EK divided by GK, which GK drops, and this gives us that the membrane potential should be equal to potassium Nernst potential, which we have already established. So what happens when the neurotransmitter is released and the ionotropic receptors open up, which means that both GK and G sodium increases because the channel that opens up can conduct both ions. So what does it mean? What should be the membrane potential? When you look at it, if GK and GA is equal, exactly equal, which means that the membrane potential should be the average of EK and E sodium. You can easily see it, because if GK and G sodium is the same thing, which means that you can say that G times EK plus E sodium divided by 2G. G's cancel out, so E potassium and E sodium plus E sodium divided by 2 is equal to Vm, the membrane potential. When you actually calculate the real values, EK is minus 80, the E sodium is around minus 60, which makes minus 20 divided by 2, minus 10. So membrane potential should be something close to minus 10-ish millivolts if the sodium and potassium conductances are exactly the same. What happens if the potassium conductance is much bigger than the sodium conductance? It means that basically membrane potential will be somewhat similar to EK. What happens if the G sodium is much bigger than GK? Which means that membrane potential should be at the steady state very close to E sodium, sodium Nernst potential. So if ratio between G's are in between these two extremes, you will find out that the membrane potential will be somewhere in between EK and E sodium. These are the upper and lower limits that you can obtain. And whether the membrane potential would be in between these two values or close to one of them depends on the ratio of the G potassium and G sodium. If the G sodium is proportionally bigger than G sodium, it moves the membrane potential, the steady state membrane potential moves towards EK. If G sodium is proportionally bigger than GK, then it moves towards E sodium. Here, the important thing is that it's not the absolute values of the GK and G sodium that's important here. The ratio of these two determines the steady state membrane potential. As a reading material, I suggest Molecular Biology of the Cell, the 5th edition. I have the 5th edition, so that's what I put in here, the page 667, starting from page 667. In chapter 11, there's a section called Ion Channels and the Electrical Properties of the Cell Membrane. That part you can read more about mass potential, the types of ion channels, how do they work, and what are the types of ligand-gated ion channels and other ion channels. And you can find more detailed information there. Okay, thank you for listening.